MSauce, Oscar here. You may have wondered, where have I been? I was supposed to upload a video on the 12th of October of 2017, and now, nearly 3 years later, I haven't. So, where did I go for this 3 years? Now, before I answer this question, what even is a year? A year has always been defined as a duration in which the Earth makes one full cycle around the Sun. This motion around the Sun is called an orbit, and every time an orbit is completed around the Sun, that is what we call a year. This definition is important because the Earth orbits around the Sun at a tilt of on average 23.5 degrees, which means that during approximately the 1st of June, the Northern Hemisphere will receive the most sunlight, which causes temperatures to be higher since more sun is hitting the Earth per unit of area due to Earth's spherical shape, and it marks the beginning of summer. The length of a day is also the longest during the summer solstice, as more of the Northern Hemisphere is in the Sun's path. Meanwhile, in the Southern Hemisphere, there is way less sun hitting the surface per unit of area. Therefore, temperatures there will be lower than in the Northern Hemisphere of the same latitude. During approximately the 21st of December, however, it receives the least sunlight due to the fact that as Earth has rotated around the Sun to the opposite side of the orbit, its direction towards the Sun has now changed, which means now the Southern Hemisphere receives the most sunlight. Meanwhile, in the Northern Hemisphere, the sun rays hitting the surface of the Earth is no longer as direct as it used to be, which means now the Northern Hemisphere is receiving less light than it did on the 21st of June. This is known as winter solstice, and it marks the beginning of winter. The length of a day is also the shortest during the summer solstice, as more of the Northern Hemisphere is in the sun's path. Now, the change in temperature, as well as a change in the length of day, means that, apart from us having to turn on the heater or the air conditioner and having our sleep cycle disturbed by the different times the sun is up, farmers will have to plant different crops due to the fact that some crops grow better in different temperatures. The energy usage will be changed since we get less solar power in the winter. Businesses will make different amounts of money, and animals such as bears and squirrels will hibernate during the winter. Along with millions of other things, this makes seasons crucial, and the cycle of seasons will need a new name, which is where the year comes from. Now, we can find the length of this orbit by using Kepler's third law formula, which states that the length between the object in orbit and the object that is orbiting it around, r cubed, divided by the time it takes an object in space to orbit, t squared, is equal to the universal gravitation constant, g, which is equal to an approximate value of 0.000000000667, which is also the average speed of the M5 in kilometers per hour, times by the mass of the larger object, m, divided by 4 pi squared. So, if we substitute the values in for our orbit around the Sun, the distance between the Earth and the Sun is approximately 149.58 billion meters. Imagine traveling that on the M5. And the mass of the Sun is approximately 1.989 million kilograms. And keep in mind, there are people who call me fat. So, reciprocate both sides, multiply both sides by 149.58 billion, and then take the square root of each side. We now have a value of t, which is equal to, in seconds, 31,558,027, which, dividing by 60, is approximately 525,967 minutes. Dividing by 60 again is approximately 8,766 hours. Dividing it by 24 is approximately 365.25 days. Leap years, of course, make up for that extra 0.25. So, it takes on average 31,558,027 seconds for the Earth to cycle around the Sun, 31,558,027 seconds for a cycle of seasons to occur, 31,558,027 seconds for us to celebrate another birthday, 31,558,027 seconds for us to receive another gift for Christmas, and 31,558,027 seconds for banks to pay you interest. Or does it? Most banks calculate interest rates per annum. Per annum, which is Latin for each year, means that each year you'll be given a certain amount of money by the bank you've deposited your money into in order for others to do the same. The amount is calculated by the money you currently have in your bank account, multiplied by the per annum percentage, which is somewhere between 1 to 3% in modern day banks. It used to be higher, but technology has improved year by year. Banks are now less reliant on having the money given by the customers, therefore interest rates have since fallen. While most banks calculate interest rates per annum, that is actually a big lie, because most banks don't give you money per year, they give it to you every month. The cash that they give to you every month is the amount of cash that you currently have in your bank account multiplied by 1/12 of the per annum percentage. Therefore, the per annum label is actually pretty misleading. So, maybe a more appropriate label will be per menses, Latin for each month, but then some banks with per annum rates of less than 1.2% will have per menses rates of less than 0.1%. And that doesn't sound very attractive for customers, does it? And in fact, who even cares? If the per menses rate is exactly 1/12 of the per annum rate, well, you get it 12 times every year. And if you get it 12 times every year, the 1/12 per annum rate will mean that you get the same amount of money as if it were given to you per year anyway. So at the end of the day, it doesn't matter. Or does it? Say I have two banks. The Eagle Bank, specialized in helping your savings soar higher, and the Saucy Bank, your number one ideal bank for helping you buy more MSauce. Now, both banks have a per annum rate of 2.4%, but the Saucy Bank, like most other banks, pay you every month, while the Eagle Bank is one of the few banks that sticks to its label and pay you money every year. Now, we have two blokes named Ed and Sed. The Sed. Now, Ed and Sed both deposit $10,000, but Ed deposited into the Eagle Bank and Sed deposited into the Saucy Bank. Now, the money that Ed receives after 1 year is 2.4% of his original deposit. Therefore, he receives $240, enough for him to take his girl out for a fancy dinner or something, simply by leaving money in a bank. Lucky man. Now, Sed, with cash given to him every month, receives only 0.2% in the first month, 1/12 of 2.4%. So he receives $20, 0.2% of 10,000. Now, in the second month, he no longer has a balance of $10,000, but an additional $20 from the interest he receives last month, for a grand total of $10,020. So in the second month, he gets a payment of $20.04, bringing his grand total to $10,040.04. In the third month, he gets a payment of $20.08, 0.2% of $10,040, with the 4 extra cents rounded off. And in the fourth, $20.12, and so on and so forth, until the 12th month, where his balance will be brought up to a grand total of $10,242.65, which means he receives $242.65, $2.65 more than Ed. Therefore, it does matter whether a bank pays interest monthly or yearly, as Sed clearly received more money than Ed, albeit to a very small scale, as that $2.65 isn't even enough money to buy, say, a Big Mac. In order for Sed to have the same amount of money as Ed while still being paid interest monthly, the Saucy Bank will have to calculate the interest based on how much cash he had at the beginning. And then after 1 year, update that amount of cash. Then it will be the same as a yearly interest, only the interest is paid monthly. But what if the interest was given more often, say per dies, Latin for every day? Well, in this case, doing the classical step-by-step method for calculating interest will be more and more tedious, so let's use a compound interest formula, which states that the amount you will receive, A, is equal to the amount you started off with, the principal amount, P, multiplied by 1 plus the interest rate, R, divided by the number of times the interest is compounded over time, N to the power of NT, T being the amount of time the money has been in the bank in years. We can confirm this formula works as plugging in N equals 1 when the interest is given once gives the value of $10,240, which is the amount of cash Ed had after depositing his money in the Eagle Bank for 1 year, calculated previously. Plugging in n equals 12 when the interest rate is given 12 times gives $10,242.65, which was the amount of cash Seth had in his bank after depositing his money in the Saucy bank for 12 months. Now, let's plug in n equals 365 to make it so that it's compounded every day for a year, that year not being a leap year. Well, it turns out our p-value ends up being at $10,242.89. So if a bloke named Ved was to save money into the very saucy bank that deposits a rate of 0.00657 per day, 1/365th of 2.4%, he'll only receive 24 more cents than Seth. If n equals 8,760, then our p-value ends up being at $10,242.90. So Ued at the ultra saucy bank, who gives interest hourly, will only receive 1 more cent than Ved, and at n equals 31,536,000, the p-value will end up slightly more than $10,242.90, but the difference is so small that they are rounded the same. So Wed at the way too saucy bank, which gives interest every second, despite receiving the interest more frequently, receives the exact same amount of money that Ued receives. So as you can see, Ed, Seth, Ved, Ued, and Wed receive more and more money respectively. However, the difference in money that they get becomes smaller and smaller. So we've clearly reached some kind of limit here. And indeed we have. $10,242.90 is the exact amount of cash that would be if n was infinite. Now, how do we know that? Well, let's look at our original formula that we used to calculate interest rates. A equals P times 1 plus R over n to the power of nt. Let's make P, R, and T 1 to maximize the simplicity of this function. Changing these values will not affect the nature of the function, so we're allowed to do that. Now, we can find what the maximum value of this would be as x approaches infinity by first logging both sides. Now we can move the n outside of the log by multiplying the entire log by n, as the log law allows us to do that. Multiplying it by n is the exact same thing as dividing it by 1 on n, so let's do that. So now we have a function in terms of log a. Now, let's try finding the value of log a as n approaches infinity. So 1 divided by a number approaching infinity is 0, so 1 plus 1 over infinity will be 1, and log 1 is 0. So the numerator is 0. Now, the denominator is just 1 over n, which will give us a value of 0. And look at this. So now we have an indeterminate form because 0 divided by 0 is not a number. The same goes if the limit turns out to be infinity or negative infinity over infinity or negative infinity. So how can we solve this? Well, we can use what's called the L'Hopital rule, which states that if a limit of a function cannot be solved and causes an indeterminate form, we can differentiate the numerator and the denominator and it will give us the same answer. So what we need to first do is differentiate the numerator of this function. So to differentiate the log function, we take the reciprocal of the function inside the log, multiplied by the differential of the function. So that will give us 1 over 1 plus 1 over n, multiplied by the differential 1 is just 0, and the differential of 1 over n is negative 1 over n squared. So this is our numerator, and for our denominator, we just need to differentiate 1 over n, which is equal to negative 1 over n squared. Easy peasy. And, oh look, the negative 1 over n squared can be cancelled out. So now this is all we're left with. 1 over n as n approaches infinity is equal to 0. So as n approaches infinity, log a will be equal to 1 over 1, which just equals to 1. So therefore, as n approaches to infinity, a will be equal to a constant value, as no matter what base the log is in, base 2, base 10, base 74, base 4.6, base pi, base 43,926,242, if log a is equal to 1, then a will be the base of the log. Now, unfortunately, we don't know what the base of the log is. So, unfortunately, we don't know what the value of the log will be. Or do we? Let's turn the tape back a little bit. After we apply L'Hopital's rule, we're differentiating the number using this rule. The differential of a log function is equal to the reciprocal of the function inside the log, multiplied by the differential of the function.
Now, that is derived from the chain rule, where it states that if a function contains a function within a function, we first differentiate the outer function in respect to the inner function, then multiply it by the inner function in respect to the pronumeral that the function is asking for. In our case, this is true because our outer function is log f of x, and differentiating the outer function in respect to the inner function gives us 1 over x, and differentiating the inner function in general gives us a differential of f of x. But hold up, if we plot the graph for the differential of log x with log base n, then as you can see, not all values of n will give a differential equal to 1 over x, except for one. 2.718, 281a, 28459, and so on and so forth. Now, why this random number between 2 and 3 that has no meaning at all? We don't know, but it just apparently happens so that the differential equation of log x with base 2.718281828484945 is equal to 1 over x. So, therefore, we know that previously, the base of our log function is 2.718281828459045, and so is the value of a. Now, you may say to yourself, big deal! This number is just some random number in which the differential equation is equal to 1 over x. What's the point? Because I'm not done yet. If you differentiate this number to the power of x, it just so happens that nothing happens to it. Even after the differentiation, it stays the same. And notice how it's the only number to do it. The famous bell curve, an important function used to calculate expected values and standard deviations, is given by 1 over the standard deviation of a certain set of data multiplied by 2 pi times by that number to the power of negative half x squared. The maximum value of the x root of x occurs at that number, and the minimum value of x to the power of x occurs at the reciprocal of that number. The square root of negative 1, also known as I, to the power of itself will give you that number to the power of negative half pi. And if you take that number and put it to a power of I times pi, you get negative 1. Keep in mind, all these applications didn't involve the log of x, the compound interest formula, nor adding that number into the equation by any way. So, why is it used for that many things? We don't know, but that's all just mathematics showing off its beauty to mankind. Mathematics is the same everywhere in the universe, and with the example of this random number between 2 and 3, maybe the universe is trying to tell us something. So maybe we should give this number a name. E. Oh, sorry about that. I was supposed to be answering where I went for 3 years, and the answer to that is... And as always, thanks for watching. Oh, I'm never gonna get tired of this, man. I'm never!